Last time we took a look at bond energy and what happens if an object is changing phase. Let's investigate the idea of thermal energy when an object is changing temperature. Based on the temperature versus energy graph we were investigating last time, if an object is changing temperature, presumably you've got, let's say you start at some low temperature, you add some energy, that raises the temperature to a higher temperature. So the graph is going to look like this. And that means that if you want to change the temperature, you have to add this energy. And that amount of energy, that change in energy, would be called the change in thermal energy, delta E thermal. And what determines how much energy you have to add? Like if you just got some object and you want to raise its temperature, what is going to influence how much energy it takes to raise its temperature? The mass is going to play a role, right? The more massive it is, probably the more energy it's going to take. What if you have an object, let's say you just have one single object. You want to raise its temperature a certain amount. That's going to cost some amount of energy. What if you wanted to raise its temperature more than that? Let's say twice as much. How much energy would that take? If you want to raise the temperature twice as much as you did before, how would that influence the amount of energy cost? Yeah, it should be twice as much energy. In general, those are going to be proportional. The change in energy required to make some transfer, some change in temperature happen is going to be proportional to the amount that the temperature changes. The more you want to change the temperature, the more energy it's going to take to make that happen. And I guess I should specify delta E thermal. So that means that delta E thermal is going to have to equal something times change in temperature, since that's one way to write out proportionality. I guess by definition, proportionality means that if you change this one by a certain ratio, a certain multiplier or divisor, this one changes by the same ratio. Like if you want to change the temperature, if you want delta T to be 3 times as much as before, you're going to need delta E thermal to also be 3 times as much as before. But you can also always write a proportionality as an equation with one of the things equaling some constant times the other thing. And that constant is what we call the heat capacity of the object, usually written as a capital C. So if you've got some object, let's say a vat of water or a block of ice or a piece of iron or something, that object has a heat capacity. That represents the multiplier that translates how much you want the temperature to change into how much energy it's going to cost to make that change happen. And as always, when we introduce a new constant of proportionality, what are some good ways to investigate that? How could we get more information about what this constant actually means? What are some good mathematical ways to explore what does this symbol actually represent? What do we usually do algebraically? If you've got some symbol that you don't know what it represents, yeah, one way is to fill in the units of measurement and explore it with that. If we have an energy equaling some constant times a temperature or a change in temperature, what are the usual units of measurement for energy? Yeah, joules or possibly kilojoules. Let's just say joules. We can always fill in a kilo later if we need to. And what's temperature typically measured in? Yeah, kelvins. So that means in order for these to match, what does heat capacity have to be measured in? Yeah, that's got to be in joules per Kelvin, joules over kelvins. That way kelvins and kelvins cancel out and we're left with joules. So that's the units of measurement we have here. Heat capacity of the object is measured in joules per Kelvin. And another way we can see that is by isolating heat capacity. If you solve this equation for C, what would you get? Yeah, delta energy, specifically delta thermal energy over delta temperature. Formally, heat capacity is heat over change in temperature, Q over delta T. But in this context, we're assuming all the heat goes into changing the thermal energy. So later on, we're going to be defining heat capacity as heat over delta temperature. But for now, we can think of that as just change in thermal energy over change in temperature. And that also gives us joules per Kelvin. So you could think of heat capacity as this ratio of how much energy per how much temperature change. In fact, you could even think of this almost like as a unit cost. For instance, since we're defining this as a ratio, what's the easiest denominator to use? What's the easiest delta T to divide by? What number would be easiest to divide by here? If you could choose just any delta T to use, what would be the easiest number to use there? Yeah, what if we just use 1 Kelvin? If you just say, assume delta T is 1 Kelvin, assume you have this object and you want to raise its temperature by exactly 1 Kelvin. In that case, delta E thermal divided by 1 is just delta E thermal. So that means the heat capacity is the delta E thermal that would cost to make the temperature raised by exactly 1 Kelvin. So that's a very useful way of thinking about heat capacity. Heat capacity is the amount of heat you have to add to make the temperature of the object go up by exactly 1 Kelvin. It's the energy cost per Kelvin of temperature increase. Or in the other direction, the amount of energy you'd have to remove to decrease the temperature by 1 Kelvin. It's symmetric, it works in both directions. It also ties in nicely to this graph. What does delta E thermal over delta temperature represent on this line? It's very closely related to the slope, right? There's only one slight exception. How do we typically define slope on a line? Yeah, the slope would be rise over run. On this graph, rise is delta temperature, run is delta energy. So the slope of this line would be delta temperature over delta energy. Is that the same as heat capacity? Or how does that relate to it? Yeah, exactly. It's not quite the slope, but it's the reciprocal of the slope. The slope of the line on the energy temperature graph is the reciprocal of the heat capacity, 1 over the heat capacity of the object, which means the heat capacity of the object determines the shape of this graph. The larger the heat capacity is, that is, the more difficult it is to change the temperature, the flatter the slope will be. So a very flat slope means a very large heat capacity. That is, it's very difficult to change the temperature. A very steep slope means a very small heat capacity. It's easy to change the temperature. And I think level of difficulty is a very good way of thinking about heat capacity. Larger heat capacity means it's more difficult to change the temperature. It takes more effort, more energy to make that happen. Any questions on the meaning of heat capacity so far? And somebody mentioned mass earlier. How does mass play into this? Like if you have two objects of different masses, how would you expect that to influence their heat capacity? Like if you have, let's say, 5 kilograms of iron and you have another block that's 50 kilograms of iron. Yeah, a larger mass is going to be a larger heat capacity, because heat capacity, once again, means the level of difficulty of changing the temperature, how much energy it costs per Kelvin of temperature change. If this is more massive, it's going to be more difficult to change the temperature. It's going to cost more energy to make that happen. Specifically, it's going to cost how much more energy? If you got 50 kilograms versus 5 kilograms of the same material, how would you expect the energy cost per degree of temperature change to compare? It could be 10 times as much. Higher heat capacity versus lower heat capacity. And yeah, it should be proportional to the mass. 10 times as much mass means it's going to cost 10 times as much energy to get the same change in temperature. So we can expect that heat capacity is proportional to mass. In other words, heat capacity is going to equal mass times something. That something is usually called the specific heat, or mass specific heat capacity, usually written as a lowercase c. So capital C is the heat capacity of the whole object. Lowercase c is called the specific heat. And that's kind of an abbreviation. It's the original term for it is mass specific heat capacity. But that's often just abbreviated as specific heat. But that's just an abbreviation. It's called mass specific heat capacity because it's the heat capacity standardized based on the mass. And what do you think that's going to be dependent on? Like if you've got two objects, let's say you've got two objects that are the same mass, a 5 kilogram object and another 5 kilogram object. Do they have to have the same heat capacity? Or what else could be different about them? Yeah, they could be different types of material, different substances. So the mass specific heat capacity is a property of the material. And typically you can look that up on a data table. If you know what substance it is, like if you're dealing with 5 kilograms of iron, you could look up the specific heat of iron on a data table, multiply that by 5 kilograms, and that'll tell you the heat capacity of that object. So heat capacity is a property of the object, including how big it is. Specific heat or mass specific heat capacity is a property of the material that it's made from. So for instance, these two objects have different heat capacities because they're different sizes, but they have the same specific heat because they're made of the same material. A very convenient way of thinking of specific heat is it's the heat capacity standardized to exactly 1 kilogram. In fact, if you isolate specific heat, if we give specific heat the same treatment, if you solve this equation for specific heat, what do you get? What would you get if you isolate it? Yeah, you get capital C divided by M, the heat capacity divided by the mass. So the specific heat of the material is the ratio of heat capacity per kilogram. In fact, we could take a look at the units there. Heat capacity is still joules per Kelvin. So specific heat is joules per Kelvin per kilogram. Or you could also write that as joules per kilogram Kelvin. Or sometimes kilojoules per kilogram Kelvin, simply because these often end up being very large numbers. So rewriting it as kilojoules is often more useful. So if you look this up on a data table, you'll typically find information listed in kilojoules per kilogram Kelvin. And we could put that all together to make one big formula for delta E thermal. Heat capacity can be replaced with mass times specific heat. So this is often, not always, but often the most useful formula for delta E thermal. The mass of the object times the specific heat of the material it's made from, those together form the heat capacity of the object, times how much the temperature changes. That tells you how much energy it costs to make that happen, how much energy you have to add to raise the temperature or remove to lower the temperature that much. Any questions on that so far? And one other thing that you might see here, we've been talking about mass as a measure of how much of the substance there is. But what's another way you can describe how much of something there is? Instead of talking about the mass, yeah, you could talk about the number of moles. You could alternatively say delta E thermal equals, instead of talking about mass, we could talk about number of moles, usually written as lowercase n. And this is more often used in chemistry and when dealing with gases, because in many cases, number of moles is easier to work with than the mass of the gas. But number of moles times, and then instead of the mass specific heat capacity, we'd have the molar specific heat capacity, usually written as C, lowercase c sub mole times delta temperature. So this is another way of writing out delta E thermal. Number of moles times the molar specific heat times the delta temperature. And in the data table, you've got, these are usually both going to be listed. You look up a material, iron or water or oxygen or whatever, it's probably going to list a mass specific heat capacity and a molar specific heat capacity. And how can you tell the difference between those? Just by looking at the values. What's going to be the difference between how those show up on the data table? Yeah, the units of measurement. Mass specific heat is going to be kilojoules per kilogram Kelvin. Molar specific heat is going to be kilojoules per mole Kelvin, or joules per mole Kelvin. And generally, you just want to use whichever one matches the units of measurement you're already dealing with. If you have an object that's with size described in kilograms or grams, use the mass specific heat. If you have an object dealing with number of moles, use the molar specific heat. So the important thing is that the units match up. And I would recommend always keeping track of units. Actually write in the units of measurement on every number you're using when you fill in the numbers and make sure they cancel out or combine properly. Any questions on that so far? Then let's try out an example. Let's say we have 5 kilogram block of iron at, let's say, 500 degrees Celsius is dropped into a very large vat full of icy slush water. So a blend of solid and liquid water, which means what temperature does that icy slush have to be at? If it's a mixture of solid and liquid, yeah, it's got to be at 0 degrees Celsius. Because if it was any hotter than 0 degrees, it would be all liquid. Any colder than 0 degrees, it would be all solid. But if it's a mixture of liquid and solid water, it's got to be at the phase change temperature. It's got to be at 0. So we take this very hot block of iron, drop it into this mixture of ice and slush, but we're assuming that it's a very large mixture of ice and slush, a very large vat of this snow. And if we've got a very large vat of snow, if we've got lots of icy water, and we drop in this block of hot iron. What would you expect to happen? Without even running any numbers, what would you expect to happen here? The temperature of the icy water will decrease, and why is that? First of all, which direction would you expect heat to flow? What's going to be gaining energy? What's going to be losing energy? If we've got cold water slush and hot iron, what happens when you put together a very hot object and a very cold object? Yeah, heat is going to flow from, heat is the flow of energy from a high temperature object to a low temperature object. Heat flows from the hot iron and into the water, because heat is always going to flow from the hot object to the cold object. So the iron is going to lose energy, the water is going to gain energy. And if we take a look on the three phase diagrams, and we should draw separate ones for the iron and for the water. So for the iron, actually for the iron, the phase change temperature of iron is much hotter than this. Melting point of iron is, what was that? Melting point, somewhere around 12 or 1300 degrees Celsius. So this iron is nowhere near its melting point. The iron starts off at 500. And meanwhile, the water where's the water here? Or where does the water start on this graph? If it's in this ice and sludge mixed phase. Yeah, it's on this horizontal line, specifically the horizontal line at 0 degrees, representing the transition between all solid and all liquid. Since it's not all solid and it's not all liquid, it's going to be somewhere in between. We don't really know exactly where in between, but somewhere in between there. And if we have these changes, we know that the water is gaining energy and the iron is losing energy. However, we know that there's lots and lots and lots of icy water slush. So once everything comes to equilibrium, what should we expect the icy water slush to look like? If there's lots and lots and lots of it. Yeah, it's going to be probably mostly liquid, because we know we're at least getting more towards the liquid side. In fact, we can tell that just from the three phase diagram. As the icy slush gains energy, it's going to be melting. It's getting more towards the liquid side. However, we know it's not going to get all the way to the liquid side because we've got a very large vat. If we had a smaller vat, if we had, and of course we need to know these specific numbers here, but if we had a small amount of slush, presumably the hot iron would completely melt it and warm up the liquid and maybe even start boiling it, maybe even turn it into a gas. But if we've got a very large vat full of icy slush, we can probably assume it's not all going to melt. So we can assume there's still going to be some ice left, maybe mostly water, but still some ice left. And so that means that it's not actually going to completely melt. It's going to end somewhere still on this chain, this phase change bar. We've got our initial point, and our final point is also going to be on that phase change bar. which means the final situation is going to be what temperature? Right, it's that same temperature, 0. If we assume that the ice doesn't all melt, that means the ice ends up, or the ice and the new liquid is still all at 0 degrees. What does that tell us about the final situation of the iron? We know the iron's cooling off. What temperature would it cool off to? If we wait long enough. Yeah, the iron is also going to cool off to 0. Because if we wait long enough, everything's going to reach the same final equilibrium temperature. The water is in the process of melting, so it's not going to change temperature. The iron's going to cool off until it's the same temperature as the water. But we know the water doesn't warm up at all. The only way for this slush to warm up is if it completely melts and then continues gaining more energy. If we know that it doesn't completely melt because there's so much of it, then that means the slush ends up still at 0 degrees, just more liquid than it was before. And the iron cools off all the way to 0 degrees because we know they reach thermal equilibrium eventually, if we wait long enough. So that's the final situation. The iron is going to cool off all the way to 0. The icy slush is going to partly melt, but not completely melt. So what's unknown here? What's a numerical value we should actually be able to solve for? What might a question about this actually be asking? If we know the iron cools off all the way to 0, we know the ice partly melts, but not completely, and we know that there's no change in temperature for the ice. What's a number we don't know here, an actual measurement we can solve for? Yeah, we could figure out the mass, specifically the mass of how much of the ice melts. We don't even know how much ice there is or how much liquid water there is, but we could figure out the change in mass. We could figure out how much of the ice turns into liquid. So let's try that. How much of the ice melts? And note that these changes in energy have to balance each other out. The iron is losing a certain amount of energy. The icy slush is gaining the same amount of energy because we're assuming these are only interacting with each other. So let's try drawing out an energy interaction diagram. We know the iron is losing thermal energy. Because of what? What's the indicator for thermal energy? Yeah, the temperature of the iron is decreasing. So that's one of the types of energy that's changing here. It looks like that's the only energy changing for the iron. The iron is losing thermal energy and that's it. Meanwhile, what's happening to the water in terms of energy? What kind of energy is changing there? Yeah, we've got a change in bond energy for the water. Based on our energy interaction diagram, is that an increase? Yeah, it should be an increase, right? It's gaining bond energy. And for the indicator for that, what's our usual indicator for bond energy? The fact that the phase is changing is conceptually what tells us that bond energy is involved. We can't really use phase change as an indicator though, because phase change doesn't really have numbers associated with it. So we are going to use mass as the indicator here. And specifically, we've got to be careful about which mass we're talking about, because we've got, like, the mass of the entire cluster of H2O is not changing. If we have 1,000 kilograms of H2O, we'll end up with still 1,000 kilograms of H2O. But it's changing how much of it is solid versus how much of it is liquid. So between those, solid versus liquid, which one of those would you consider the higher energy state? Yeah, liquid is the higher energy state. So I would use mass of liquid, how much of the water is liquid in terms of kilograms, in order to, as the indicator here. Part of the reason for that, as this partially melts, what's happening to the amount of liquid? Yeah, the amount of liquid is increasing. And note that that matches the fact that the bond energy is increasing. As long as you're using the higher energy state as the indicator, then these arrows should match up. For example, if we were freezing it instead, if we were going from liquid to solid, we would still use mass of the liquid as the indicator. But as you're freezing it, what would happen to the amount of liquid? Yeah, we'd be losing liquid. The amount of liquid would decrease, which corresponds to the bond energy decreasing if you're freezing it. So as long as you're sure to use the mass of the higher energy state as your indicator, these arrows should match up. And that looks like the only types of energy involved here, because the water is only changing phase. There's no change in temperature of the water. Any questions on that setup so far? And we should even be able to list out the initial and final values here. Let's say iron starts off at an initial temperature of 500 degrees Celsius and ends at a final temperature we know of 0. As for the water, we don't really know how much of it starts off as a liquid. Let's just call that capital M. And then the final amount, we don't know either, but it's going to be more than M. So we start off with some amount in liquid phase, we end up with more than that in liquid phase. And that's the whole system. Would you consider this to be an open system or a closed system? And why is that? What would make this an open system? Or why would we consider this to be an open system? Does this say anything about heat being exchanged with the environment? It doesn't really specify, right? I mean, if we just take a bunch of snow and drop some iron into it, I would expect the air around it to play a role there. But let's say we want to make it so that doesn't happen, because if it does, that's going to make it very unpredictable. If we want to make it so we just have the iron and the snow or slush or whatever just interacting with each other, how could we design the experiment to make sure that that doesn't interact with the environment? How could we make it a closed system? Yeah, let's put it in a thermally isolated container, put a lid on it and pack it with insulation. Let's say instead of just putting it in like a metal box or something that allows heat to flow, let's put it in an ice chest with lots of insulation. So let's say a very large insulated vat. A very large insulated vat so that the iron and the slush are only interacting with each other, no heat flowing into or out of the system. That way we can treat this as a closed system. Which means, what do we know about the total energy in a closed system? What can we say about total energy in any closed system? The total energy equals 0. The whole system has no energy at all. Well, if it doesn't have any energy, not much is going to happen. We don't want to say it has no energy. What do we want to say about the amount of energy? It's conserved, which doesn't mean it equals 0. It means it's a constant. So we don't want to say the energy is 0. We want to say the energy is a constant, which means the change in total energy is 0. this is what you want to start with. Don't get mixed up between energy versus change in energy. We don't really care how much energy the system has. What we care about is how much the energy changes. And in a closed system, we can assume that the change in the total energy is nothing at all. That the total energy, it has energy, but the total energy doesn't change. Or if it's an open system, delta E total would equal the changes, heat plus work. So in any open system, delta E total would equal heat plus work. It's just that in a closed system, there is no heat or work, so delta E total would equal 0. There's no change to the total energy. So this is true in general for any closed system. In this particular case, we can expand delta E total into these two changes added together. Delta E thermal for the iron and delta E bond for the water. So those changes have to add up to 0. That matches the idea that one of them is increasing the amount that the other one decreases. And we can now fill in some formulas. For delta E thermal, we could use the MC delta T formula we were looking at earlier. Mass of the iron times specific heat of the iron times delta temperature of the iron. And then for delta E bond, we can use the formula we were looking at last time. Delta M of the water times delta H, the latent heat of water melting. And one of the other advantages of using the higher energy state is that when you subtract final minus initial, the correct positive or negative sign automatically shows up. If you subtract a larger mass minus a smaller mass, you're going to get a positive value. However, in this case, we don't really need to worry about that so much. We don't really need to know how much liquid we started with and ended with. We just want to know how much of the ice melts. So instead of treating delta M as final minus initial, I would just treat delta M as the variable we're trying to solve for. We want to know how much mass changes phase. So delta M is our goal. And everything else, I think we can find values for. Like we know the mass of the iron is how much? Yeah, that was given as 5. And specific heat of iron, where can we find that information? Where can we get information about the specific heat of some material? Yeah, we could look that up on a data table. So if we check a data table, such as, for instance, this one, then we look for iron, heat of melting. Does this not include heat of melting for iron? That's quite an oversight. Then let's backtrack and just pretend we were talking about copper the whole time. So this copper that we've been using all along, because who would ever use iron for anything, has a heat of melting of, looks like it lists 2 values. Actually, we don't want heat of melting, we want specific heat, right? Lists two values for specific heat. So which one of those should we actually use? Or how would we decide which one? Yeah, we take a look at the units. And it looks like we have units of kilojoules per Kelvin mole or kilojoules per kilogram Kelvin. Which one of those makes the most sense in the context of what we have here? Yeah, kilojoules per kilogram Kelvin, so we'll use that, 0.386. So specific heat of copper, which we've been using all along, is 0.386 kilojoules per kilogram Kelvin. And I think that's the main piece of information we're going to need. Although also, while we've got this data table here, what other information should we look up? Yeah, the heat of melting, because we're going to also need to worry about the delta H for water. So delta H for water melting. And it looks like we've got heat of melting. Heat of melting, again, it lists two values. We're talking about kilograms, so we'll just use kilograms. Heat of melting for water, that's this 333.5. So delta H for water melting, 333.5 kilojoules per kilogram. And I think that's all the information we're going to need. Let's go through and correct any mistaken references to iron. That was actually copper all along. Yeah, copper the whole time. So we're trying to find these ones. So it looks like we have all the other numbers. We know the mass of the copper. We looked at the specific heat of copper. We looked up the delta H for water melting. Also, what's the delta temperature for copper? How would we calculate that delta temperature? We could fill in 5 kilograms. We could fill in 0.386 kilojoules per kilogram Kelvin. And yeah, the delta temperature, -500, because you can always find deltas by subtracting final minus initial. 0 minus 500 is -500. And that's degrees Celsius, but we have kelvins here. Can we just change the change in Celsius into a change in kelvins? Or how would you usually change Celsius to Kelvin? What's the usual conversion? Yeah, if we add 273 to both of them, what's going to happen when we subtract final minus initial? If you've got final plus 273 minus initial plus 273, what happens to those 273s when you subtract? Yeah, those are going to cancel out anyway. So you don't actually need to worry about whether it's Celsius or Kelvin. If you're talking about a change in temperature, decreasing your temperature by 500 degrees Celsius is the same as decreasing your temperature by 500 Kelvin. So even though we were thinking of this in terms of degrees Celsius, we can write the change as -500 Kelvin anyway. Celsius and Kelvin are interchangeable as long as you're talking about a change. If the formula had a temperature in it without a delta, it has to be in Kelvin. But delta temperature, Celsius and Kelvin are interchangeable, as long as you're consistent about it. Then we also have this unknown delta N. We don't know how much of the mass changes phase. That's what we're trying to find. Times delta H for water, 333.5 kilojoules per kilogram. And we can also cancel out some of the units here. We've got kilograms and kilograms canceling out. We've got kelvins and kelvins canceling out. So it looks like we just got 5 times 0.386 times -500, and that'll be in kilojoules, plus 333.5 kilojoules per kilogram times delta M. And then all that's left is solving for delta M. Whatever this turns into, add that to both sides, divide both sides by 333.5 kilojoules per kilogram. The kilojoules will cancel out. You should be left with kilograms. And that value, that should be a positive value that tells you how much of the ice turns into liquid water, how much of the slush melts. Any other questions on that? On the setup or the general concept? All right, try using the same approach on some other practice problems. You've got several on your FNT you can use, or if you want some more advanced practice, I also have a worksheet on, if you go to math.andcheese.org/P7A, there's a worksheet of more practice problems on conservation of energy with thermal energy and bond energy. So give that a try. Let me know if you have any other questions, and I will see you next time.